so far? We start talking about different types of proofs. Objectives, proofs. So, well, when it comes to theorems, when it comes to statements, we have different methods proving them. How to prove a statement? Sometimes you can use direct proof. What's the meaning of that? It means that you can use the definitions and prove that statement. Direct proof. Usually we use the definitions. Some other times you can use the contrapositive of the statement, if then, not conclusion, then not hypothesis. Contrapositive. Some other times you can say that, hey, what if the conclusion is not correct? What do we get by having a wrong conclusion? The conclusion is wrong, and in this case, it results in a contradiction with some simple facts. So we have different methods proving something. When it comes to existential statements, if you can find one example, you're done with the proving of that statement. For example, let's go over some of the important ones. So this theorem says the only divisors of 1 are 1 and negative 1. Okay, so we have a statement. It says the only divisors of number 1 are 1 and negative 1. How do we prove this? Prove. Suppose not. Suppose other than 1 and negative 1, we have other divisors. So suppose not, and we have other divisors for 1, other than 1 and negative 1. Let's see what happens. There you go. So when we're talking about the divisors of 1, it means that we're looking for factors that when we multiply them together, we get 1. So let me see what I used here. Let m and n be divisors of 1. So what's the meaning of that? It means that m times n is equal to 1, and at the same time, since these two are divisors of 1, m divides 1, n also divides 1. Okay, perfect. So what do we have in this case? M divides 1, it means that by definition, there exists another factor like S belongs to Z such that 1 is equal to MS. N divides 1, it means that there is an integer like T belongs to Z such that T times N is equal to 1. Okay, these are the meanings of being the factors or divisors of 1. Okay, Let's analyze this. At the same time, here we have m times s. Here you have t times n. Both of them, when you multiply them together, equals to 1. Okay, now think about it this way. We're looking for two integers, that when you multiply them together, the result is equal to 1. Note that we're not working with real numbers. We only work with integers. So m and n are positive numbers, are integers that when you multiply them together, the result is equal to 1. M and s. So what are the multiples that when you multiply them together, it is 1? It can be 1, or both of them are negative 1. When you multiply them together, the outcome is equal to 1. Okay, now take a look at this. If m is equal to 1, m is equal to 1, so we're just connecting what we're writing in detail to the outcome here. If m is equal to 1, you have 1 times n equals to 1. So this n must be 1 as well. What about this? What if m is equal to negative 1? If m is equal to negative 1, in this case, we get negative 1 times n times an integer equals to 1. The outcome is fixed. The outcome is 1. So in this case, your n is equal to negative. So m is 1, n is 1, n is negative 1, n is negative. The same for here. If t is in z and t times n is equal to 1, you can say that, hey, the multiples of t and n is equal to 1. So you have only two options. The same here. 1 times 1, negative 1 times negative 1. We don't have any other options. So this shows that our conclusion is that we cannot find any other divisors for 1, except for 1 and negative 1. Okay, another theorem. So this theorem says, suppose you have integers, like a, b, and c. These are all integers. Suppose a divides b, so a divides b, and b divides c. The transitivity says that a divides c as well. Okay, how do we prove this? A divides c. We have the definition of divisibility, so let us use direct proof. Proof by definition. We know that A divides B. What's the meaning of that? It means that we can find another integer like s such that B is equal to AS. We also know that B divides C. B divides C. What's the meaning of that? It means that we can find another integer like T such that C is equal to BT. Well, first equation says B is equal to A times S. In the second equation, I have B. So I'm going to substitute that in the second equation. So it means that C can be written as AS times T. AS times T. Well, What's the meaning of that? It means that C is equal to A times an integer. C is equal to A times an integer. It means that A divides C. So A divides C. The proof is done. Next theorem says, prove that any integer is divisible by a prime number. So we're just reviewing the proofs. Theorem. Prove that any integer greater than 1 is divisible by a prime number. Okay, so let us begin. Proof. So we're going to use common sense and the definition of prime and composite number and divisibility. What are we going to do? We're going to consider an integer like n. Let n be an integer. So I'm just going to write down the way that we think about proving this theorem on the right-hand side so you know how to break down the numbers. When you select a number, any number, this number can be prime or it can be composite. All right, any number. You can select 2, 3, 5, 7, 11, 13, and the rest of them. It can be prime or it can be composite, like 4, 6, the rest of the composite numbers. So you're randomly selecting an integer. You have two options. The first option is if n is prime, we don't have anything to prove. Why is that? We're trying to show that any integer greater than 1 is divisible by a prime number. If that integer that we randomly selected is prime, so obviously it's divisible by itself. If not, if n is not prime, it means that it's composite. It means that you can find at least two numbers, like r sub 0 and s sub 0, such that n is the multiple of those two numbers, r sub 0, s sub 0. Okay, and at the same time, we know that r sub 0 divides n and s sub 0 divides n. And both of them are in between 1 and n. This is how we define divisibility. Okay, now we start. Which case is this? Is this the case that n is equal to 6, 2 times 3? Or is this the case that n is equal to, for example, 4 times 25, 100? Which case is this? We cannot exclude all of these cases. So we have to think about general case. So for n equals to r sub 0, s sub 0, we have two options. If either r sub 0 or s sub 0 are prime numbers, then you're done. You don't have anything to prove. What if not? What if R sub 0 and S sub 0 are both composite numbers, like this case, 4 and 25? If not, and R sub 0, S sub 0 are composite numbers, it means that R sub 0 can be written as the multiplication of two other numbers. R sub 0 can be written as R sub 1, S sub 1, and S sub 0 can be written as the multiplication of two other numbers, and we have to repeat this loop. Repeat the process. When you repeat this process, you eventually, at some steps, you get to the step that the multiplication includes at least one prime. So, when we continue this process, it stops at some point. We eventually can find a prime number that belongs to one of the divisors or factors of n. So we write it this way. We write n as the product of integers that at least one of them is prime. So we're done. One of the important definitions is quotient remainder theorem. Quotient and remainder theorem. This theorem says, suppose you have an integer, for an integer like n, and a positive integer d, we can find two unique integers. There exist two unique integers Q and R such that n can be written as dq plus R, and R is between 0 and d. So any number, any integer like n can be broken down into sum of two other integers. Like 6 can be written as 2 times 3 plus 0. 5 can be written as 2 times 2 plus 1, and so on, the rest of the numbers. So when you're referring to n div, positive integer d, we are referring back to our Q, but when we write n mod operator, D, we are referring back to remainder. Remember that in Python or in other coding languages, this is written by using the percent sign, the mod operator or percent sign. Okay, so let us use this new theorem and prove something. Here we go. We have a nice theorem. This new theorem says the square of any odd integer, so the square of any odd integer has the form (8m plus 1) for some positive integers like m. M is positive integer. Okay, so how do we prove that? The square of any odd integer. Let us try the direct proof. Use the definition. We're going to start by having an odd integer. Proof. First of all, note that by using quotient remainder theorem, any integer like n can be written as follows. That n can be written as 4 times q, or n can be written as 4q plus 1, or n can be written as 4q plus 2, or n can be written as 4q plus 3. The quotient remainder theorem says any integer can be written as d times q plus a remainder r, and this r is in between 0 to d. In this case, our d is equal to 4, so your r is in between 0 and 4. So n can be written as 4q plus 0, n can be written as 4q plus 1, n can be written as 4q plus 2, and n can be written as 4q plus 3. Why I'm doing that, why I'm selecting 4? Because this theorem says it is 8m plus 1. I'm looking for 8. If I square the odd values, I get 4 squared, which is 16. So somehow I can end up with 8. 16, 2 times 8, so I can create 8. That's why I'm selecting D to be 4. I'm not selecting D to be like 3 or D to be 2 or other numbers. Okay. Since n must be odd, the acceptable forms are n equals to 4q plus 1 and n equals to 4q plus 3. Okay, perfect. Then the theorem says square it. N squared is equal to 16q squared plus 8q plus 1. And if I square this guy, I get n squared equals to 16q squared plus 24q plus 9. Very well. Okay. Let's see what do we have. Here, if I factor out 8, I get n squared equals to 8 times 2q plus 8, q plus 1. This value, this quantity, is just an integer. So n squared can be written as 8. I'm just going to call this m, 8m plus 1. What about this guy here? N squared is equal to, here I have 9. I'm going to break down 9 as 8 plus 1. So I get 16 q squared plus 24 q plus 8 plus 1. Between these, I'm going to factor out 8 and create my m. So n squared is equal to 8 times 2 q squared 3q plus 1 plus, and this is my m. So n squared is equal to 8m plus 1. And return. The square of any odd integer has the form 8m plus 1. 8m plus 1. So this is just q, 2q squared plus q. I wrote 2 here, thank you. Perfect. So next theorem. This theorem says there is no greatest integer. There is no greatest integer. Okay, the proof is very simple. Proof, suppose not. Suppose not. And we have the greatest integer, which is equal to m. In the search of integers, greatest integers, I found m, and I say, hey, m is my greatest integer. Well, so m is the greatest integer, and m is, for example, greater than 1. Of course, you know that. This is the greatest integer possible. So what I'm going to do, I'm going to do some algebra. I'm going to add some numbers. Well, let us add 1 to both sides. What do we get? 1 plus 1 is 2, less than m plus 1. Hey, I found another integer which is 1 unit greater than my greatest integer. We found a new integer m plus 1, which is 1 unit greater than our greatest integer. So it means that m is not the greatest integer. We found another number which is greater than our greatest integer. So the proof is done. Conclusion, m cannot be the greatest integer. So the theorem is proved. Let us continue. Here. Square root of 2 is irrational. Square root of 2 is irrational. Okay, perfect. Proof. Suppose not. Suppose not, and square root of 2 is a rational number, belongs to Q, or rational numbers. So it means that square root of 2 can be written as the division of two numbers, a divided by b. A and b are both integers, and b is not 0. Now what I'm going to do, I'm going to write this fraction in reduced form. So this is a very important step. Important. Let us write a and b in reduced form. Let a divided b be in reduced form. What do I mean by that? Remember that, for example, if you have 4 divided by 6, it's not in reduced form. The reduced form is 2/3. They don't have any common factor. 2 and 3 have no common factor. So we wrote 4/6 in a reduced form, 2/3. This is what you learned from algebra. We just simplify this fraction, you write it in reduced form. What's the reduced form? 2/3, no common factor between 2 and 3. So there is no common factor between A and B. Very well. Now, square root of 2 is equal to A/B. It means that B times square root of 2 is equal to A. Okay, this is important. Now I'm going to square both sides. 2b squared is equal to a squared. What's the meaning of that? It means that 2 is a factor of a squared. So 2 is a factor of a squared. It means that 2 is a factor of a. It means that a is even. So a is equal to 2k. I'm going to go back up here and get this done. So I'm going to get back here and substitute this guy over there. 2b squared is equal to 4k squared. It means that b squared is 2k squared. It means that 2 divides b squared. It means that 2 divides b. Two divides b squared and 2 divides b. It means that b is equal to 2l. Okay. B is 2l, a is 2l. What's the meaning of that? It means that a and b have a common factor 2. This is our contradiction. So A and B have common factor. But we assume that A and B have no common factor. So what's the meaning of that? It means that we cannot assume square root of 2 is a fraction. We cannot assume square root of 2 belongs to rational numbers. It means that square root of 2 is irrational. Okay, perfect. A proposition for you. These are useful propositions. This proposition says for any integer a and any prime number p. So for any integer n and any prime number p, if p is a factor of a, then p cannot be a factor of a plus 1. So if p divides a, then for sure we can say that p cannot divide a plus 1. Well, let us prove this. True. Suppose not. Suppose not. And p divides a plus 1. So what do we have here? We have p is a factor of a, p is also a factor of a plus 1. So what's the meaning of that? By using the definition, we can find an integer like s, that a can be written as p times s. Now what's the meaning of this part? It means that we can find another integer like t, such that a plus 1 is equal to pt. Okay, here we go. So I have two equations. A is ps and a plus 1 is equal to pt. I have two equations. I'm going to subtract these two equations. Let's see. So I have a plus 1 minus a equals to pt minus ps. What's the meaning of that? It means that 1 is equal to p times t minus n. It means that 1 is equal to a prime number times an integer like m. Is it possible? You have a prime number, prime, 2, 3, 5, 7, and so on, and m is just an integer. It's not a fraction, so you cannot cancel out these two, which is impossible. Impossible by the definition of prime number. Remember that the multiples of 1, the factors of 1 are 1 and 1, negative 1 and negative 1. But this is a prime number. It is greater than 1. So it's impossible by the definition of prime number. It's a contradiction. Where did it come from? It came from that if we assume the conclusion is wrong, we get to a contradiction. It means that the theorem is, this proposition is true. So your conclusion since we got a contradiction by assuming P divides A plus 1, it means that P cannot divide A plus 1. Okay, in this theorem, we want to show that the set of prime numbers is not finite. So here. The set of prime numbers is infinite. There you go. How do we prove that? Suppose not. So here you have your proof. Suppose not. What's the meaning of that? It means that if you assume you have set of prime numbers, it stops somewhere. So you have 2, 3, here you have 5, 7, 11, and it stops at P. Suppose P is the largest prime number. So what are we going to do? Let Q be the product, the multiplication of these prime numbers. Q be 2 times 3 times 5 times P. We're not sure if Q is prime or not, but what do we know? We know that P as a prime number divides Q. So P divides Q. P is a factor of Q. Well, now think about it this way. In previous proposition, we say that if P divides N, then P doesn't divide A plus 1. We just proved this. We're going to use this. So P as a prime number divides this multiplication. We already proved that P cannot divide Q plus 1. Okay, P is not a factor of Q plus 1. So what's the meaning of that? It means that if I add 1 to Q, then there is no prime number dividing Q plus 1. So what's the meaning of that? P divides Q, P doesn't divide Q plus 1. If I add 1 to this number, it's either a number that you saw before or something new. You add 1 to it, and P is not a factor of Q. We assume that this set is finite. So what's the meaning of that? It means that this is just a number, Q plus 1. It means that we can find another number since P doesn't divide Q plus 1. We can find another prime number that divides Q plus 1. And that prime number is greater than P. is greater than. But we assume that this is the largest prime number that we have. It stops somewhere. So there's a contradiction. We have a contradiction. Where did it come from? It came from the assumption that P is the largest prime number. So conclusion is there is no largest prime number. It means that this set goes on and on infinitely.